All right, well, I will get started. So, we begin with a word of prayer. Ahem. I'm going to start. Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to bless our steps today. Help us to understand a little bit more about your creation and just glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me get this stuff out of the way here. We're not there yet. So we have Newton's second law, right, to work with now. F equals to ma. F is the net force, right? So we'll talk more about that. So we have the net force on a mass is the mass times the acceleration. This is Newton's second law. Okay, so example 1. Let us suppose that we have like a cat.
Evil cat?
That's redundant. Yes, of course it's evil. We have a cat, and the cat's position is at, I don't know, 3 meters, 1 meter. All right, so it's 3 meters, 1 meter. That's the center of the cat. And then we have some different actors pulling on the cat. All right, so suppose you got a rope here, right? A rope, and on the one hand you've got one dude down here, Mr. Top Hat, and he's pulling down with a force of, let's say, 30 newtons directly that away. And this is a top-down view, so like this is, you know, this is all the horizontal plane we're looking at, all right? So gravity's not going to come into play here. And we're also going to assume, like, there's no friction to think about at the moment. We'll come back to friction after the first test, okay? So we've got 30 newtons pulling that way. And then you have a ghost over here, and it is pulling at, let's say, 100 newtons. And let us suppose that this angle here is given to be 80 degrees. All right. Then here's the question. If the cat is in equilibrium, what force is applied by Elon? So you can kind of picture Elon's over here somewhere, right? So here's the force that's applied by Elon is over there, and I'm not sure. We'd like to know the magnitude and direction of the force that's applied by Elon, right? I learned something yesterday. Do you guys know who Wernher von Braun is? Famous Nazi scientist. We brought him into our space program. He built many of the liquid rockets that fueled this, NASA program early on. Part of this larger Operation Paperclip, where we took Nazi scientists and put them into our ranks. Anyway, he wrote this science fiction book in like the late 40s, I think. And in that book, he describes a civilization on Mars, a so-called technocracy, that's ruled by a class of 10 people, the leader of which is called the Elon. So it was prophesied by Wernher von Braun over 50 years ago that Elon Musk would be the future ruler of Mars. Okay, I added the Musk, but it serves my purpose. So, all right, anyway. So if it's in equilibrium, what's that mean? So we know that the acceleration is 0, right? So we know that the sum of the forces must be 0. Now the forces are equal to what? We got ourselves a 0 minus 30 newtons. That's Mr. Top Hat downward, right? And how about the ghost force? What's that? I got 100 newtons times what? It's a negative, right? Minus 100 newtons times. If this is 80 degrees, then there's 10 degrees down here, right? So I could do minus 100 newtons times the cosine of 10 degrees using trigonometry. And on the other hand, the y component of the ghost force is positive, right? So I've got 100 newtons times the sine of 10 degrees for that. It's kind of puny, but there it is. That's the ghost force. And then the force we don't know, the Elon force over here, which I've just called F. I guess I'll put an F sub E on it for E for Elon. There you go. Hooray. Okay, so apparently the Elon force must be equal to, what we got? 100 newtons times the cosine of 10 degrees. I solved for FE. Oh. And then 30 newtons minus 100 newtons times the sine of 10 degrees. And so I subtracted the vectors to the other side there, guys. That's what I did. So the Elon force apparently is, whatever that is. What we got? Oh man, I'm still back in the quadratic equation solver mode from the other day. That's not going to work. All right, computation 100. Cosine, am I in degree mode? I am, that's good. 100 times cosine 10 is about 98.48. Okay, well there's that. 98.48 newtons for your x component. And then what have I got? I got 30 minus 100 times the sine of 10.
Would it be negative since, like...
No. And this is, I'll return to your question in just a second here, but I think I'm right. But I could be wrong. Let's try again. Okay, so what are you asking me?
Like, would it be negative since, like, cosine of 10 is really in the second order almost?
Well, the 10 degrees is technically right here. So I'm just using that as a reference angle, and I'm putting in the sines by hand. Yeah. I mean, you could have done cosine of 170, and that would have put the minus in there for you. But I just chose to put the minus in by hand, right? Like you could also, if you don't like this, you could say, well, it's really 100 newtons times the cosine of 170 degrees, because I refuse to work in anything except for standard angles. And I wouldn't take that from you if you wanted to do that, because 90 degrees plus 80 degrees is the standard angle of the ghost force. And that would automatically inject that minus that I put there. But, yeah. Okay, so that's the Elon force. What's the magnitude? Square root. 48 squared. 12.64 squared. What's that give us? I get a 99.29-ish newtons. And what's the standard angle? Well, this one it's in quadrant 1, right? So we can actually just plain old use inverse tangent. Yep.
When we're solving for magnitude, are we alright just writing like the force of E, or do you want us to put the magnitude bars around it?
Our notation is that without the vector, it's the magnitude. So,
okay.
Yeah.
We need the magnitude.
This is by definition the same as this.
Okay. Thank you.
So, in a textbook or something, they might use bold for the vector, whereas unbold is the magnitude. But I don't know how to write bold on the whiteboard, so this is our system of notation. Anyway, so the angle is just inverse tangent of y over x in this case because we're in quadrant 1, so it's just that easy. 12.64 divided by 98.48, inverse tangent that thing. Whatever that is, that's your standard angle here. Of course, you can't always just use inverse tangent like this. This is because we're in quadrant 1, we're able to just do this. Whoa, really? Okay. So 7.314 degrees is the standard angle of the Elon force. So there you go. Of course, you could also say Elon is pulling with 99.29 newtons at 7.314 degrees north of east. All right, give me a second. I will fix that. But before I do that, let me give you the next problem. So example 2. Let us suppose that we have, this one's a little bit more adventurous. So what I'm going to do is I'm going to draw like a pole here and a pole over here and one over here. All right. And I want to suppose that there's like a ball in the middle. All right. So if I drew this from the top down, it would look like this. My one pole is here, the other one's here, and the other one's here, and the ball is in the middle, like this. I need to give coordinates on these things. I will in a second. I'm probably going to regret this example. I reserve the right to bail on this in about 2 minutes if I don't like the way it's going. So let us suppose that the one pole is at the origin, right? The other pole is, let's say, at the base of the pole is at like I don't know, 100 meters, let's say. We can make it 10 meters. Maybe 10 meters is less ridiculous. So let's make this at this distance here, 10 meters, and I'll make this distance also 10 meters, right? And I'll say that the height of these poles is, how about 10 meters? Sound good? Okay, fine. I heard a no. 20 meters it is. So every one of these poles also 20 meters tall. All right. And all right. So like in terms of a three-dimensional coordinate system, let's see here. In terms of a three-dimensional coordinate system, omitting meters for the sake of not being annoying, this point right here would be 10, 0, 20. This point up here at the top of the pole would be 0, 0, 20. The point at the top of this pole would be 0, 10, 20. All right? And I guess to make this problem make sense, I need to tell you where this point, I want to pick a point here. Let's see here. I probably should put this at something like, let's suppose it is at, I don't know. Let's try for 5, and let's say it's 10 meters up, all right? That's where this ball is. So you got this ball hanging on cables, right? And we're going to ignore the mass of the cables. And this is in equilibrium, all right? So the question I want to ask is, what's the tension in these cables? What's the tension in these cables? So like this is cable 1, cable 2, cable 3, right? So if this is in equilibrium, what does that mean? Right, the sum of the forces are 0. And what are those forces acting on that ball? Yeah. 3 different tensions. We got those. And gravity. Very good. So, like, let's say like T1, T2, T3, and then of course gravity, right? Which is like minus mg z hat, right? 0, 0, minus mg. Now m here, of course, would be the mass of the, let's say the bowling ball, you know? So I'll make it a capital M. I'll give it some feet. That way we won't confuse it with meters. So m with feet is equal to, oh, I don't know, 10 kilograms. Great. All right. So how would we do this? Let me write it out symbolically. And I'm probably just going to start this problem. I'm not going to finish it. But what we need is the sum of the tensions, right? And then plus gravity to be equal to, you know, m times a, which is equal to what? 0 if it's not accelerating, if it's in equilibrium. The question then is, how do you quantify these tensions, right? So the tensions have to act along the direction of the cable. I'm assuming that these cables are really taut, so they're just straight lines between the bowling ball and their point of attachment, right? So it's a little bit unphysical because actually cables droop and stuff, but it's a pretty good approximation. So T1 is something like, T1 as a vector is T1 the magnitude times T1 hat, right? And T2 as a vector is T2 times the magnitude T2 times T2 hat. And T3, tension is T3, the magnitude T3 times T3 hat, right? But I would point out to you is we can figure out the direction of T1 and T2 and T3 given the data that I give you, right? See, because like T1 hat should be parallel to what vector? It should be parallel to the vector what? T1 goes from this point to that point, right? It should be parallel to the vector I get from like 10 minus 5, 0 minus 5, and 20 minus 10. In other words, T1 should be a unit vector in the direction of 5 minus 5, 10. So like T1 hat, a formula for it straight up is 1 over the square root of 25 plus 25 plus 100 in the 5 minus 5, 10 direction. All right. T2 should be parallel to what? Well, T2 hat should be parallel to what? It should be parallel to, let's see here, 0 minus, so minus 5, 0 minus, so minus 5 minus 5, and then I got 20, 20 minus, where was I? Yeah, 20 minus that coordinate, which is 10. So this is the direction vector. So I'm calculating the direction vectors from the top of the poles to the bowling ball is all I'm doing. So 20 minus 10 is 10. So this tells me that T2 hat would be like 1 over the square root of 150 in the, you know, minus 5, 10 direction. And finally, T3 hat should be parallel to what? We want to go from here to here, right? So I do 0, I do 0 minus 5, 10 minus 5 is 5, 20, and then finally 10. So apparently T3 hat would be 1 over the square root of 150 times minus 5, 5, 10. So I was supposed to, my 5s gradually get worse and worse the further down the board I write. This is just how it is, so I'm sorry about that. All right, so at this point, the problem is essentially solved. Not really, but At this point, it should be clear that you could solve the problem. Why? So all you have to do is go up in here and put T1 times that T1 hat, T2 times T2 hat, T3 times T3 hat, right? You're given M, you're given G, you have this vector equation, right? So you have three equations, three unknowns. The unknowns are the magnitudes of the tension, 1, 2, and 3. So you can solve it. Yeah. I'm not going to do that because there are other things I want to show you today besides this example, but I hope that illustrates a method for you. Your homework problem is easier, right? In the homework, I ask you to find like the tension. There's just two cables, and it's all in a plane. So you can just use trigonometry to solve the problem in the homework about tension. Lest I forget, let us take attendance. I see I have added a 124 column. So if you can add a 129 column, we'll do a 2 for here. It's very exciting, yes? All right, so that's all I got to say about that example. Now, so past this point, you can do algebra to solve for the tensions. My next example is a little bit easier. Actually, I really should use the projector for what follows here. I don't even, I've got so many chords up here. This is it, maybe. Write out one more here. So example 3. Weight is mg, right? So weight is the mass times gravity. So weight is a planet-dependent thing, right? The weight of something on Earth is different than the weight of something on the moon, right? Like Earth gravity and moon gravity, I think the moon's like 1/6 of Earth's gravity, right? So if you were to stand on a scale and it was, say that scale said that you weighed 60 pounds on Earth, right? If you were to take that same scale and somehow take it to the moon and stand on the scale, you would then only weigh 10 pounds, right? Your mass would be the same in both categories, but the weight would be different. So we pretty much always talk about mass in terms of weight in English, right? Because like we talk about pounds. Pound is a force, actually. What is the English, or the British, if you will, unit for mass? Anybody know? Kilograms is the metric unit for mass. So slugs, yeah, slugs, but no one knows. But somebody, I'm saying you don't exist apparently, but I just said you're no one. What's that? They teach you that in engineering? Oh, good, good. All right, well, I don't need to talk about it here anymore then. Very good. So, for example, if we have a bear, and this bear's, weighs, let's say 250,000 newtons, that's a lot. Then on Earth, what's its mass? The mass of the bear is what? The weight, which is 250,000 newtons, divided by g, which is 9.8 meters per second squared, which works out to 25,510 kilograms. All right, so we need to be aware of the difference between weight and mass. Weight is a force, mass is not. But they're related by multiplication by g. Let's see here, another example. So, all right, I think we've done enough equilibrium examples. Let's do some non-equilibrium examples, all right? How about example 4. You observe R of t is equal to alpha t, comma, beta t squared, and then gamma, I don't know, cosine of alpha t. Great. If the object has mass m, find the net force. So how do we do this?
You have to take the derivative of the position twice to get the acceleration.
Okay, yeah. So dr dt is what? The velocity, right? So that's what? In this case, it's alpha 2 beta t minus alpha gamma sine alpha t. Here I'm, of course, assuming alpha, beta, and gamma are constants. And then acceleration is dv dt. And so we differentiate again. We get ourselves a 0, 2 beta, and then minus alpha squared gamma cosine alpha t by the chain rule, right? Finishing move, the net force is equal to the mass times the acceleration, which in this case is 0, 2 beta big M, comma, minus alpha squared gamma big M cosine alpha t. And there you go. That's all you do. So this is an easy problem. Somebody, if I give you a position and ask you to find the net force, this is not hard, all right? It's not hard.
Alpha,
Yeah.
beta, and gamma are just
Constants. Alpha, beta, gamma, constants. I said that, I didn't write it, but you know, constants. I put them in because I don't want to write stuff like, you know, 10 meters or 3 meters per second. So you think of alpha being like a 10 meters, and you could think of like the beta being, you know, 10 meters per second squared or something. So I need constants like that to be fussy in order for this to be dimensionally consistent, which is why I do this sort of thing. But anyway, so that's an example. Another example I should give you guys. I like this one. No, I have to project this one. If I write this one out by hand, it'll be the rest of class. So I better project it. I better do that. See if I can get this thing working. Oh, it's on standby. Well, I'm going to request in the strongest of terms to not teach in this classroom next semester. This classroom is cursed. All right, let's see here. Where was I? Somewhere in here, I have my notes. So my next example is actually, I give Ron Swanson a pair of rocket boots, and then we study his motion. So I'm kind of proud of this example. It of course has a requisite, you know, I had some art for it too, so we have that to enjoy. Let's see, are we allowed to turn off the lights today? Let's see if I can make it big enough for us to see. Oh, the double scrolling, it got me. Not the double scrolling. All right, here we go. This is my example 3.2.14. Oh no, have we not moved the camera at all today? Oh, I have been assuming you guys were moving it. That's bad. Oh well. It's my fault. But anyway, I think I talked through it pretty well. So sorry, people not being here. Oh well. Anyway, 'tis what it is. So here we go. This. Can you guys even see this? All right, good. Well, you're doing better than I am. So as you can see, I have put Ron Swanson with appropriate rocket boots here. And so this is the problem. He has a pair of rocket boots with thrust vectoring. The boots create a constant thrust of 3 times Ron's weight during operation. Ron begins at rest and boosts vertically for 3 seconds, then boosts at an angle of 45 degrees for another 4 seconds. Then Ron falls under the projectile motion. The question is to find the horizontal distance traveled by Ron. So I'm assuming all of this motion happens in some plane, right? Otherwise the question doesn't make sense. So I'm talking about 45 degrees, like above the horizontal. So during stage 1, you got gravity pulling down, right? And he's also going vertically with thrice his weight, right? So the upward force is 3 times weight, which is 3 mg. So there's your boot force there. So to start with, he's accelerating upward at twice gravity. And I say that happens for 3 seconds, right? So my final velocity after those 3 seconds is 0.58.8 meters per second. And the position happens to be 0.88.2 meters. Great. Then at stage 2, we assume that the thrust boots point the force in the 1-1 direction. So so the boots are pushing him up like that, which means that, of course, the actual vectoring of the thrust is the opposite way, right? So basically rockets push off the air, or they eject stuff, and then conservation of momentum makes them go the other way. But we don't know about momentum yet, so whatever I said, who knows? But we'll get there. But anyway, so the thrust force is like in this direction. And so then, of course, we're still against gravity. So during the second stage here, when he's at 45 degrees, that's his net force, which gives us this acceleration after we divide by the mass. And as such, we have another 3 seconds in that boost. No, 4 seconds in that boost. So from 3 to 7 seconds, we get, the velocity after the second stage of the boost is this, and the position after the second stage of the boost is that. And those work out to, respectively, it's really loud. It's really, really bright. Got to close my eyes next time. Nope. I didn't wait long enough. All right, so anyway, so we plug in those numbers and out pops the second velocity, the final velocity here after the boosting is done. And here's his final position. Then stage 3, the boots are off and he's up in the air and he's got an initial position and initial velocity, right? So what happens is he just keeps coasting under projectile motion from that point. So the third step, we have an acceleration of just, 0 minus g. And so then, again, project kinematics gives us these equations. And we can figure out when he hits the ground by looking for where y is equal to 0 again. And you solve that quadratic equation. You get 2 solutions. One is minus 3.44 seconds. The other is 24.41 seconds. Obviously, physically speaking, we're interested in the 24.41 seconds. So after the rocket boots turn off, he's gliding through the air for another 24.41 seconds. And then I put that into my formula for X stage 3, and out pops, well, he goes about 2 kilometers. So 2,196 meters. Pretty nice pair of boots, So yeah, of course we're neglecting things like, lots of things, but if there was such a thing as rocket boots and they, there you go. All right, so that brings us to the next topic, which is the necessity of inertial coordinate frames for Newton's laws. So, two coordinate systems R1 and R2, are said to be inertially related, all right? If there is a constant rotation matrix R and constant vectors C and B for which R2 is equal to R times R1 plus TB plus C. Now this TB plus C basically allows the origins of the two coordinate systems to be related with respect to one another by constant velocity motion. See, that's what this part of the formula is basically saying. The origins of the two coordinate systems are related to each other by constant velocity motions. That's what's contained in that mathematics. R is a fixed vector. So what I'm saying is that we want to allow the possibility for two inertial coordinate systems to be related to each other by a fixed rotation, right? Like, we should be allowed to use coordinates, if you could imagine this, instead of using, like, you know, the corner of the room and the edges of the bottom of the room as like axes, right? We ought to be able to take those and like rotate them 30 degrees and, you know, have the axis, have the axis like this and the other one like that and the other one like that, right? We should be able to just do a fixed rotation of the axis. That should still define a coordinate system where the laws of physics can be written, right? So that's a freedom we would like to allow ourselves in describing what's an inertial coordinate system. And so I know that, like, I'm not going to test on the mathematics here because you guys don't know rotation matrices. Not all of you have had 221. That's something you ought to understand after you've taken Math 221. It's like how to multiply a column vector by a rotation matrix. But I know that's outside your mathematical scope. Nevertheless, physics demands this freedom. All right, so good news is I'm just going to tell you the calculus. So here it is. So R2 is the second observer. R1 is the first observer. We're looking at a physical situation, and we're observing a physical, like some events in terms of two perspectives, like the coordinate system 1 and the coordinate system 2. What I'm describing now is how are their velocities related. So how would you relate the velocities? You simply differentiate the given positions. So if I differentiate this formula up here, we just have dr2 dt equals r times dr1 dt plus b. The constant vector, that differentiates to 0. And this gives us that, you know, the second velocity is equal to the rotation of the first velocity plus this b. Now this b right here, that is the velocity of the coordinate of the origin of the first coordinate system with respect to the second. See, if I put r1 equals to 0, that gives me r2 is equal to tb plus c. That describes where r1 equals to 0 in the r2 coordinate system. So basically, this b is the velocity of the first coordinate system as measured by the second coordinate system. Anyway, so this is the relation between the velocities. And then if I want to relate the accelerations, well, I differentiate again. And when I do that, I get a2 is equal to r times a1. So two inertially related coordinate systems, the accelerations have to just be related by, at most, a fixed rotation. Right? So think about Newton's laws. What is Newton's second law? It says F equals ma, right? So if I take one inertial coordinate system, I write down F equals ma. I want to write down Newton's laws in the second coordinate system. What can you tell me about the net force in the second coordinate system? If it's 0 in the first coordinate system, it must be what? It must be 0 in the second coordinate system, right? And more generally speaking, the rules then for writing Newton's laws in the rotated coordinate system would just be that you have to rotate the force. So like if we had Newton's law obeyed in the first coordinate system, m1a equals to f1. If I multiply this equation by the rotation matrix, it gives me that m times, you know, r times a1 is equal to rf1. And so in order for Newton's laws to be consistent, we would have to have the relation that if I have a force, right, in one coordinate system, it must be that that same force is represented by just the rotation of it into the second inertial coordinate system. All right, that would be what would be required for Newton's laws to be consistent, right? So anyway, that's just a quick overview here of the idea of coordinates. Now, I wanted to tell you this section 3.31, I say here you can skip it in the first reading, but this 3.31, what it does is it explains what happens if the two different coordinate systems are possibly related by a rotation matrix which not just constant, maybe it changes with time. So these would be examples of non-inertially related coordinates. And it turns out that if the coordinate systems are not inertially related, the relation between the accelerations is not simply a rotation, it's rather messy, all right? But if you study these equations carefully, you can derive things like the Coriolis effect and other rotated frame effects. The only one really we look at in here is the circular motion. That's the only place where we do an accelerated frame besides, that's the only rotated frame thing we do in here, is circular motion. So anyway, you can skip that section is my point. All right, but this one matters. This section matters. Here's the big difference. Now I'm looking at two coordinate systems, all right? And the thing is, these coordinate systems, do you notice what's missing, like relative to the last discussion? Now I'm just assuming that both coordinate directions, they're both in the same, the coordinate axes they're oriented in the same way. I don't need any rotation to get from the coordinate axes for my first observer or my second observer. I'm saying that they share the same direction for x and the same direction for y and the same direction for z. It's just that the origin for one and the other is shifted. All right, so like, in other words, you could parallel translate this x-axis to the x-bar axis. You could parallel translate the y-axis to the y-bar axis. You could parallel translate the z-axis to the z-bar axis. What another way to say it, x hat is equal to x bar hat. Y hat is equal to y bar hat. Z hat is equal to z bar hat. They have the same unit vectors. All right, that's what we're assuming. Suppose that's the case. You have two coordinate systems like that. In that case, we have the rather simple formula that the position measured relative to the S frame is equal to the position of the barred frame, R naught, plus the position relative to the S bar frame. So I'm using frame as a collective term for coordinate system. Every problem we've done in here so far has worked in a frame. The examples I did in class worked with a fixed frame of coordinates. We actually used that frame explicitly in my example too, right? I wrote down x, y, z. We measured coordinates with respect to an origin and displacements from that origin. That's a frame of reference, a coordinate system. So if we have two frames, which I'm calling collectively S and S bar, we can relate the position in S to the position in S bar, simply as that. And if we do that, we have, RS is equal to R naught plus RS. And so then, how are the velocities related? Well, differentiate this equation. If we differentiate this equation, you get that the velocity in the S frame is equal to the velocity of the origin here, plus the velocity measured with respect to this S bar frame. And if you differentiate again, we get that the acceleration in the S frame is equal to the acceleration of the origin of the S bar frame plus the acceleration measured with respect to the S bar frame. So, as I say down here, since Newton's second law holds in S, because we're assuming at the start of all this that S is an inertial frame, which is one, Newton's laws are written for fixed frame, like a fixed frame of reference, right? Like, we don't write down Newton's laws if the frame of reference we're looking at is accelerated. We can't write down Newton's laws in an accelerated frame of reference. We have to have a frame of reference which is just sitting there, or in constant velocity motion. All right, it cannot be accelerated if we're going to write down Newton's laws. So we are assuming at the outset that Newton's laws are written with respect to a fixed frame of reference. So given that, we have the mass times the acceleration in the S frame is equal to the net force. Well, if you put this together, it says that the mass times the acceleration in the possibly moving frame, let's say S bar is the moving frame, it's equal to the net force in the unmoving frame minus the mass times the acceleration of the moving frame. So this means that if we're in a moving frame that's accelerating, effectively the net force is different. This is called the frame effect. So I can show you some examples of that in just a second, but so you have a few homework problems that are based on this. Not the acceleration part, but like the velocity part. The velocity part's really simple. If you have a moving frame of reference, you want to calculate the velocity, with respect to the moving frame of reference, you just have to add the velocity of your frame which is moving, plus the velocity that's measured with respect to the moving frame. Classic example, you're on a train, right? It's moving 50 miles per hour that way. You throw a baseball on the train 10 miles per hour the other way that it's going, right? What's the speed, what's the velocity of the ball that you measure with respect to the ground's frame of reference? 40, right? Because you have to do 50 minus, minus 10. Because if you're, well, anyway, let me show you the example. So here's a silly example. You have a river which has a speed of 0.55 meters per second. A student swims upriver against the current a distance of 1 kilometer, then swims back to where he began. If the student can swim at 1.1 meters per second in still water, then how long did his swim in the river take? So there's two parts, right? He swims up the river against the current 1 kilometer. Well, what's his effective speed if he's swimming against the water with respect to the the river bank, the fixed frame of reference of the Earth? He's really only swimming 0.55 meters per second, right? Because he's going against the water. He's always, he's not actually swimming at 1.1 meters per second relative to the bank of the river. He's only swimming at that relative to the bank. So how long does it take him to go a kilometer at that speed? Well, I don't know. But it says in the notes here, so you do, the change in position divided by, man, this is annoying, velocity, which is 0.55, and you get, I think, 1,818.2 seconds to get to a kilometer upstream, right? Then he turns around and he swims back. On his way back, he's swimming with the current, right? Which means his effective speed relative to the bank is not just 1.1 meters per second. It's actually 1.65 meters per second. But I've had a minus here because we've chose, upstream to be positive direction and downstream to be negative direction. So that's his speed downward. And so how much time does that take? Well, that takes 606 seconds, a lot less time, right? And so you add those two times together, you got, that's the total time that it took him to make this swim. That's how long. So this is all based on the simple formula I wrote a second ago. I thought I had what happened to I thought I had another art thing here. Oh, here it is. So like here, we'll end class. I started class a little bit late again because there's like this endless stream of distractions at the start of class by the tech people here. It's really getting on my nerves. We have a bear stands on the elevator, which accelerates upward at acceleration g. We find the weight of the bear on the scale, considering the elevator is an accelerated frame of reference with acceleration g. So relative to the frame of reference that co-moves with the elevator, the bear's acceleration is 0. It's just sitting there in the elevator, right? But the forces on the bear include the force of gravity, but also the weight of the scale, the force on the scale. The scale pushes up on the bear, gravity pushes down, right? And so the normal force is that scale force in this case. So we have the net force minus the mass times the acceleration of the moving elevator. I keep saying accelerator. So minus mg plus the weight minus mg has to be equal to 0 because, it's not accelerating in the frame of reference of the elevator. So effectively, the weight, it doubles the bear's weight, right? If the elevator is accelerating up at acceleration g, it would tell the bear he's twice as heavy as he actually is. Other extreme, the elevator's going down at g. It's free falling. What's the weight of the bear? 0, right? So if you feel weightless in an elevator, then you know that you're accelerating down at the acceleration due to gravity, right? I have never had that problem in the elevator in this building. In fact, I'm not even sure that the elevator in this building accelerates. It's a very good example of it. Like, feels like constant velocity. I don't know, but I'll shut up. See you guys Friday.